This is the Aero 320 final project, done by Saeed Raouf, Greg Arnold, James Perez, and Marco Salazar. For this project, we had to select a dynamic system and explain how it works. The system could either be natural or man-made. So what is our chosen dynamic system? The dynamic system involved is any spacecraft that is controlled and propelled by the cold gas thruster system and its associated sensors. The figure on the right shows a cold gas thruster system inside a spacecraft. What is a cold gas thruster? A cold gas thruster is a type of rocket engine which uses pressurized gas to generate thrust. Cold gas thrusters are most often implemented as part of a three-axis reactive control system. As opposed to traditional rocket engines, no combustion is required to produce thrust. Its design mainly consists of a tank, nozzle, propellant, and regulating valves. The valves are controlled electronically through a controlled system. Normally, solenoids are used as control valves. Due to low levels of thrust requirement, the mass of the system is extremely small compared to the traditional combustible rocket engines. Both mass and dimensions of the system vary a lot depending on its application, the amount of delta V required. On average, the mass is less than 200 pounds, while width and length is less than 3 feet both. So looking at the history of cold gas thrusters have been frequently used in small satellites since the 1960s. They are used to perform orbit maneuvers, maintenance, and to control attitude. The system is usually used to create small changes in velocity less than 50 meters per second. It has proven to be the most suitable and successful low-thrust space propulsion for LEO maneuvers, due to its low complexity, efficient use of propellant which presents no contamination and thermal emission, besides its low cost and power consumed. Alternate to cold gas thruster is the resistojet. The major difference between them is in their thermodynamics. Resistojet follows isothermal conditions, while cold gas can follow both isentropic and isothermal. However, cold gas system is preferred over resistojet as it promises safety. Resistojet uses heating elements that can melt during the operation, which increases safety risks. Now let's look at the governing equations of the system. Due to the complexity of this system, there are different equations required to design each part of it. To find the fuel required to cause a certain change to velocity, we use the rocket equation. For pressure vessel consideration, we use isentropic equations and the ideal gas law. Similarly then, for the nozzle design, the following equations are used. Here, the subscript T refers to the throat of the nozzle, 2 is used for the exit area, and 1 represents the inlet area of the nozzle. Once the nozzle design is done, mass flow rate is then calculated using the equations below, and from that, kinematics of spacecraft are determined using the kinematic equations.
So what type of system is this? It is a pressure-based continuous system. During operation, every variable of the system is continuously changing. Each differential equation involved is time-dependent. Key quantities that change during the operation of the system are temperature, pressure, mass, velocity, both angular and linear, and the density of gas.
Now, what are the inputs to this system? The propellant used is the only input. All the gases shown in the table are used as cold gas. However, nitrogen and air are preferred due to cost and total impulse per unit volume. Nitrogen is mostly used in cases where extreme low temperatures would cause icing around the other components.
So what is the output of the system? Thrust is the primary output. As mass exits the system, thrust is generated through conservation of momentum, propelling the body forward. As a result, acceleration, velocity, and displacement change. So what quantities are being measured? During operation, the following quantities are continuously measured by onboard sensors. The graphs show expected behavioral trends of said quantities, which were constructed with the governing equations discussed previously.
So let's see how the cold gas thruster system actually works. The system is divided into 2 sub-pressure systems, a high pressure and low pressure. This diagram below shows a low pressure system. Low pressure is used to control the high pressure system. As we can see from the diagram that there are pressure actuators at the right end. The dotted line from the actuators is to show that they are connected to high pressure system. So to operate the high pressure system, solenoids in the low pressure system open up, letting the pressure pass through them, and this helps in opening the pressure actuators so the pressure from the high pressure system can actually pass through them. So once the pressure passes through the actuators in the high pressure system, it is blocked by the solenoids before the nozzles that are seen on the right side of the diagram below. These solenoids are controlled individually by the communication system based on what we are using the system for. For attitude control, a particular solenoid would open up to provide thrust in a certain direction, which then led the spacecraft to reach a desired orientation. For most orbital maneuvers, all 4 solenoids open up at the same time. Let's see how all the components when put together would look like. The CAD below shows the arrangement of the high-pressure system, but as it is obtained from Cal Poly Hyperloop, it only shows one nozzle, which is due to their own design purpose. But for spacecraft, there are going to be 4 nozzles fitted at 4 different corners.
So what is the feedback of this system? As the thruster system is utilized for various purposes, the feedback is based on the action being performed, whether it be attitude control or orbital maneuvering. In the case of attitude control, the feedback receives data from the reaction wheel if the wheel is struggling to provide complete attitude control. The feedback system will open the desired thruster to rotate the spacecraft to the desired orientation. For orbital maneuvering, when the feedback system receives the signal, it acts as a PID controller to calculate the measured quantities over time to prevent from overdraining tanks or going below recommended temperatures. Microcontrollers are usually used as feedback controllers. They control the solenoids. The microcontrollers are part of the communication system. When a signal is received, they open and close the valves accordingly. So how does control law look for this feedback loop? The algorithm issues instruction to the microcontrollers, which pass on commands to the solenoids. Simultaneously, pressure and temperature sensors attached to the solenoids are collecting data to inform the algorithm about when to close the valves.
The performance metrics of the system takes into account the attitude control, which is the system's ability to support the reaction wheel to place the spacecraft in the correct orientation, orbital maneuver, which is also the system's ability to cause the spacecraft to change the orbit, but only used for small orbital maneuvers, heat management. Cold gas thruster actually reduces the need for a heat management system in spacecraft, which is required for combustive systems. And finally, the electrical energy, which is also minimized by using this system. Finally, we are going to talk about the coordinate frames involved in locating the system at all times. 3 different frames are used: body fixed reference frame attached to the spacecraft itself, Earth inertial reference frame, and finally the reference frame at the location of the tower from where the spacecraft is being observed. And that concludes our presentation.